Imagine a factory that has almost everything. The steel is there. The software is loaded. The workers are ready. Tens of thousands of parts have arrived from around the world. And yet the line is slowing down because one small component has not. Inside that component is a material most people never think about, perhaps a rare earth magnet, a strip of copper, or a carefully purified battery chemical. It may represent less than 1% of the machine's final value. But without it, the machine is not unfinished. It is useless. This stopped being a hypothetical in 2025. After China placed export controls on several medium and heavy rare earth products, some manufacturers outside China cut production or paused lines while they waited for licenses and material. For more than a century, oil shaped the map of power. It fueled armies, built fortunes, created alliances, and made distant conflicts matter to people who could not locate them on a map. Now a new map is emerging.
Lithium for baterias.
Copper for grids. Cobalt for batteries and jet engines. Rare earths for the magnets inside motors, turbines, missiles, and machines. They are being called the new oil. But that phrase hides the most important part of the story. These materials are not one market. They are not burned once and gone. And the country with the biggest mine is not always the country with the most power. Because in the mineral age, the map is not just where the rock comes from. The map is the chain. The word critical sounds geological, as if certain elements are simply scarce and the rest are not. That is not how governments actually use it. A mineral becomes critical when two things meet. A society depends on it, and its supply is vulnerable. That vulnerability can come from concentrated mining, concentrated refining, few substitutes, long project timelines, or the fact that the mineral is produced only as a byproduct of something else. So the list changes with technology and politics. Copper joined the final American critical minerals list in 2025. The element did not change. The assessment of economic and security risk did. Now look at the chain. First, a deposit has to be found, financed, permitted, and mined. Then the ore or brine has to be concentrated and chemically converted. Impurities are removed. Elements that behave almost identically have to be separated. The material is turned into a metal, an alloy, a cathode, a wire, or a magnet. Only then does it enter a battery, a motor, a transformer, or an aircraft. Each stage creates a different map. In 2025, Australia was the largest LITHEE, a miner, in the published global table, with about 32% of the displayed total. But China refined 74% of the world's LITHEE. Chile mined 23% of the world's copper. China refined 47%. The Democratic Republic of the Congo mined about 3/4 of the world's cobalt. China refined 76%. And China held both sides of the rare earth chain, about 69% of mine output and 85% of broad refining. Those numbers describe production in 1 year, not ownership of every deposit. But they reveal where leverage can concentrate. A nation may have and still lack the chemical plants, power, ports, skilled workers, customer relationships, and years of experience needed to turn it into a precisely qualified material. That is the first way the new oil analogy breaks. Oil moves through large, comparatively fungible global markets and is consumed when used. Critical minerals are a collection of different markets. They remain inside long-lived equipment. Some can be recovered. Some can be replaced. A new battery chemistry can weaken demand for cobalt while strengthening demand for LITHEE, graphite or phosphate. A better motor can use less rare earth material, but perhaps more copper. so nobody can literally own the periodic table. But countries and companies can control its junctions. And the first junction is the one now moving faster than almost any other, the battery. Lithium begins in landscapes that look like different planets. In the high Andes, mineral-rich brine sits beneath salt flats. It can be pumped, concentrated, and processed into lithium chemicals. In Western Australia, lithium comes from hard rock. The ore is blasted, crushed, and concentrated before traveling onward for chemical conversion. Both routes end at the same demanding destination, material pure and consistent enough to survive inside a battery for years. In 2025, the published world mine total was about 290,000 tons of contained lithium, excluding a withheld United States figure. Australia produced 92,000 tons. China produced 62,000. Chile produced 56,000. But at the refining stage, China's share was 74%. That gap is the story in miniature. Australia can lead at the mine while another country dominates the conversion of concentrate into battery-grade chemicals. The rock matters. The refinery determines when the rock becomes useful. Demand is real. Batteries represented 88% of global lithium use in 2025. Electric vehicle batteries alone reached about 1.2 terawatt-hours of deployment, nearly 30% more than the year before. But strategic importance does not guarantee a permanently rising price. The annual average real price of battery-grade lithium carbonate fell from roughly $63,700 per ton in 2022 to about $9,000 in 2025, an 86% collapse as new supply arrived faster than consumption. Then the market turned again. From January 2025 to April 2026, lithium prices more than doubled. Boom creates a rush of projects. Bust delays them. Then the next surge in demand discovers that mines and conversion plants cannot be switched on like software. There is no simple geological countdown here. The United States Geological Survey estimated 37 million tons of lithium reserves in 2026 and roughly 150 million tons of measured and indicated resources. Bolivia's famous 23 million ton figure belongs to the resource category, not the reserve column. Reserves are not all atoms in the ground. They are the portion considered economic under current conditions, and they change. The more urgent question is whether projects can be built responsibly and on time. Lithium production can require substantial energy, land, infrastructure, and water. But one viral number cannot describe every mine. Hard rock, conventional salt flat evaporation, geothermal brines, and direct extraction use different processes in different watersheds. A 2026 study of one operating in 22 proposed American lithium mines found that, in most of the studied subbasins, projected available water was insufficient under many mid-century scenarios. That finding is serious. It is also specific to those American basins, not a universal coefficient for every ton of lithium. Producing countries are asking another question. Why export only the raw material? Chile's national strategy is state-led, but it uses public-private partnerships, environmental protection, and consultation. It is not a blanket seizure of every lithium project. Zimbabwe took a sharper step in February 2026, suspending exports of raw minerals and lithium concentrates while planning a move toward lithium salts and other processed products. Both are attempts to climb the chain. And the next metal shows why that climb matters even when the element is anything but new. Copper is so familiar that it can disappear into the background. It is in the wire behind a wall, the winding inside a motor, the coil inside a transformer, the bus bar inside a data center, and the cable connecting new power to the grid. Batteries store electricity. Copper carries it. In 2025, the world mined about 23 million tons of copper and produced about 29 million tons of refined copper. Those are different stages, not two piles that can be casually added together. Chile led mine production with 5.3 million tons. The Democratic Republic of the Congo produced 3.2 million. Peru produced 2.7 million. Together, those three countries supplied just under half of displayed world mine output. China mined about 1.8 million tons, roughly 8% of the total, but its refineries produced about 14 million tons in the United States Geological Survey table. In the International Energy Agency's Harmonized Series, China held 47% of global copper refining. Again, the mine map changes at the refinery gate. Copper's problem is not that the planet is about to exhaust the element. The 2026 reserve estimate was about 980 million tons, with much larger identified and undiscovered resources beyond that. The problem is timing, grade, capital, infrastructure, and social permission. A new copper project takes about 17 years on average from discovery to production. That clock includes exploration, technical studies, consultation, permits, finance, construction, and the slow ramp-up of a huge industrial system. A price spike today cannot travel backward through 17 years. Under the IEA's July 2026 outlook, announced mine projects would leave a copper supply gap of about 25% in 2035 relative to demand in its scenario. That does not mean the world wakes up one morning with 1/4 of its copper missing. It means the project pipeline, if it does not change, is not large enough for the projected market. The pressure is already visible in an unlikely place. Smelter fees. For 2026, benchmark copper treatment and refining charges fell to $0 per ton, while some spot charges had been negative since 2024. That does not mean refining costs nothing. It means smelting capacity has been competing fiercely for constrained copper concentrates. The bottleneck can move from one link to another. There are escape valves. Aluminum can replace copper in some cables and heat exchangers. Fiber replaced copper in much of telecommunications. Better design can reduce material intensity. Scrap matters too. In the United States, old and new copper scrap together supplied roughly 30% of copper supply in 2025, an American figure, not the global recycling rate. But substitution is engineering, not magic. Aluminum behaves differently. New cable designs need new equipment and standards. Recycling needs collection and clean feedstock. And all of it takes time. Copper is the giant volume challenge of electrification. Cobalt is almost the opposite. A smaller market in which two concentrated stages and one unusual economic fact can move the whole world. Most cobalt does not come from a cobalt mine. Approximately 99% is produced as a byproduct of copper or nickel mining. That means a high cobalt price may not create much supply if the host mine does not make sense. The operator is usually deciding whether to produce copper or nickel, with cobalt arriving beside it. This ties three markets together. It also helps explain why cobalt can respond strangely to a shock. In 2025, the world mined an estimated 310,000 tons of cobalt. The Democratic Republic of the Congo produced 230,000 tons, about 3/4 of the displayed total. Indonesia, the next largest producer, supplied 44,000. Then the geography changes. China refined 76% of cobalt in 2025. That does not mean China legally owns 3/4 of Congolese rock, or that every shipment follows one national route. Mines have different owners and contracts. Material moves through complicated trading networks. The safe conclusion is simpler. The most concentrated mine stage and the most concentrated refining stage sit in different countries. In February 2025, the Congolese government temporarily stopped cobalt exports. In October, it shifted to quotas. The United States Geological Survey recorded an allowance of 18,125 tons for the remainder of 2025, then up to 96,600 tons a year in 2026 and 2027, including 9,600 tons for a national strategic reserve. Those numbers were current to the 2026 USGS summary and should be treated as a dated policy, not a permanent law of the market. But the effect was immediate enough to matter. Cobalt prices rose by roughly 130% between January 2025 and April 2026, driven largely by the Congolese restriction. There is a human story inside that market, and it deserves more care than a montage of suffering. The International Labor Organization says more than 100,000 people work in artisanal and small-scale cobalt mining in the DRC. A monitoring system had registered more than 6,200 children in mining in Haut-Katanga and Lualaba. Children have performed dangerous tasks. Adults have worked in unstable pits with weak protection. But it is false to say that every ton of Congolese cobalt is mined by children, or that all industrial operations are identical to artisanal sites. Sweeping claims erase the difference between documented abuse, legitimate livelihoods, and efforts to formalize the sector. A serious response includes safer work, traceability, enforcement, income alternatives, and remediation for children, not simply turning away from the country. Cobalt also demonstrates how technology can weaken a choke point. Lithium iron phosphate batteries contain no cobalt. In 2025, LFP supplied more than 55% of global electric vehicle battery deployment. Other battery chemistries have also reduced cobalt intensity. Yet cobalt has not become irrelevant. Batteries remain its leading global use, and in the United States, superalloys, mainly for aircraft gas turbine engines, accounted for 51% of domestic cobalt use in 2025. The material can lose ground in one application and remain essential in another. Rare earths take that idea further. Their strategic power comes less from the amount in a product than from how difficult they are to separate and how difficult they are to replace when performance matters. Rare earths are not one thing. They are a family of 17 elements with different markets and different jobs. Some help create powerful permanent magnets. Others go into catalysts, phosphors, lasers, sensors, or specialized alloys. And despite the name, many are not unusually rare in the Earth's crust. The difficulty is finding deposits that can be mined economically, then separating elements that behave almost like chemical siblings. The mine is only the beginning. Mixed or becomes concentrate. Concentrate becomes separated oxides. Oxides become metals. Metals become alloys. Alloys become precisely manufactured magnets. Each transformation needs equipment, chemistry, energy, waste control, skilled operators, and customers willing to qualify the output. In 2025, world mine production was about 390,000 tons measured as rare earth oxide equivalent. China produced 270,000 tons, or about 69%. The United States produced 51,000. Australia produced 29,000. At the refining stage, China's share of the broad rare earth market was 85% in the IEA's harmonized data. You may also hear a number above 90%. That describes a narrower high-risk, magnet-related processing chain in the IEA's risk framework. 85 and over 90 are not interchangeable claims. One covers broad rare earth refining. The other focuses on the most strategically exposed part of the system. The United States offers a revealing contrast. It was the second largest miner in the 2025 table, yet it remained 67% net import reliant for rare earth compounds and metals. Mining or at Mountain Pass did not, by itself, recreate every missing link to a finished magnet. That matters because compact rare earth magnets deliver remarkable performance. They turn electricity into motion in vehicle motors and industrial robots. They help wind generators turn motion into electricity. They also appear throughout defense systems. The United States Department of Defense identifies rare earth materials in F-35 aircraft, Virginia and Columbia-class submarines, drones, Tomahawk missiles, radar, and precision-guided munitions. Its public figures from March 2024 said an F-35 contains more than 900 pounds of rare earth elements. That is total rare earth content, not 900 pounds of one magnet, but the scale explains why defense planners talk about a complete mine-to-magnet chain. Building a second chain is expensive. The IEA estimates that diversifying rare earth magnet supply will require around $60 billion of investment over the next decade. By 2035, projects outside the leading producer could deliver roughly 50,000 tons of mining, less than 40,000 tons of separation and refining, and only about 18,000 tons of metals, alloys, and magnets. Notice how the numbers shrink at every step. That is the magnet empire. Not simply a territory containing but a ladder of capabilities that fewer places can climb. And when one country dominates the top rungs, a material worth almost nothing compared with the finished machine can become a global choke point. Put the four maps on top of one another. Australia leads lithium mining, but China leads lithium refining. Chile leads copper mining, but China leads copper refining. The DRC leads cobalt mining, but China leads cobalt refining. And in rare earths, China leads both mining and processing, with even greater concentration in the magnet chain. Across the IEA's key energy minerals, the average share held by the leading refiner reached 70% in 2025, up from 68% in 2020. Excluding rare earths, the leading share still rose to 72%. And from 2023 through 2025, the top refining countries accounted for more than 3/4 of the growth in refined supply. This concentration did not appear because of geology alone. Refining and separation reward scale. Plants need reliable power, chemical suppliers, transport, waste management, engineers, and nearby manufacturers. A processor that sits beside cathode plants, battery factories, motor makers, and export ports can improve faster than a lonely new plant on another continent. For years, many importing countries were comfortable buying the cheapest material available. Some midstream businesses carried thin margins, difficult permitting, and visible environmental burdens. China invested across those stages, built supplier clusters, trained workers, accepted industrial costs, and developed customer relationships. Policy mattered. So did scale, timing, and the choices of buyers elsewhere. Calling it all a secret master plan is too simple. Calling it a normal market with no strategic consequences is also too simple. Concentration can be wonderfully efficient in calm times. One cluster produces at enormous scale. Costs fall. Manufacturers use just-in-time inventories. Capital is not wasted on duplicate plants. Then a border closes, a license slows, a mine floods, a war begins, or a government changes the rules. Efficiency becomes a single point of failure. The paradox is that the material itself may be cheap relative to the product it controls. Critical minerals make up roughly 1/4 of the cost of a battery cell, but only about 3% of the average electric vehicle's price. Rare earth material can represent around 40% of a magnet's cost, yet less than 1% of the vehicle. Copper may be 10 to 15% of the price of a transformer or power cable. In one IEA sensitivity test, tripling rare earth prices added only about 1/10 of 1% to the price of a car. Tripling battery material prices added around 5% to an electric vehicle or storage system. That sounds reassuring until the material is unavailable at any price. A tiny input can have a small cost share and a total operational importance. The loss is not the price of the missing magnet. It is the value of every car, turbine, radar, or robot that cannot be completed without it. This is why the 21st century contest is not only a race to mine more. It is a race to build redundancy in the middle of the chain. And it is why governments have started treating trade measures that once looked technical, an export license, a quota, a customs code, as instruments of power. Not every restriction is a weapon, and not every weapon looks like a ban. An export tax raises the price of sending material abroad. A quota limits the amount. A licensing system decides who may ship to whom and for what use. A prohibition closes the gate. A strategic reserve removes supply now in order to preserve it for later. Those distinctions became impossible to ignore on April 4, 2025. China placed export controls on specified products containing 7 medium and heavy rare earth element groups: samarium, gadolinium, terbium, dysprosium, lutetium, scandium, and yttrium. Exporters had to apply for licenses and disclose end users and end uses. China's official rationale was national security and non-proliferation. The rules were not a blanket ban on all rare earths. China's Ministry of Commerce has said eligible civilian applications can be approved. But licensing can still create delay and uncertainty, especially when companies have little inventory and few alternative suppliers. The IEA reported that some automakers outside China reduced utilization or paused production after the April measures. In October 2025, China announced a much wider package, including controls with extraterritorial reach over some foreign-made products. That expansion was then suspended for 1 year. As of August 9, 2026, the broader October package was due to remain paused until roughly November 2026, while the April controls remained in force. That status is deliberately dated. In a market shaped by notices, licenses, and negotiations, current has a short shelf life. The scale of possible exposure is enormous. The IEA estimated that full implementation of broad rare earth restrictions could place $6.5 trillion a year of downstream output outside China at risk. That is a conditional scenario, not money already lost, and not the value of the rare earth market itself. It is the value of all the products whose supply chains pass through the choke point. China is not the only state changing the flow. The DRC used a cobalt ban and then quotas. Zimbabwe suspended raw mineral and lithium concentrate exports to push processing at home. Other governments use taxes or minimum prices to collect revenue or encourage domestic industry. The OECD's 2026 inventory, which covers the years only through 2024, found that product country export restrictions on critical raw materials had increased 5-fold since 2009. In 2022 through 2024, about 16% of global critical material trade faced at least one restriction, up from 12.4% in 2009 through 2011. The instrument matters. Of new measures in 2024, 38% were licensing requirements, 25% taxes, 24% prohibitions, 12% quotas, and 1% minimum price measures. When governments stated a rationale, revenue generation accounted for more than 47%. Security is part of this story. So are industrialization and public finance. Trade law has struggled with the tension. In an older case, the World Trade Organization ruled against Chinese rare earth export duties and quotas, which China removed by May 2015. That case did not decide the legality of the 2025 licensing controls. In another case, a WTO panel found against Indonesia's nickel ore export ban and domestic processing requirement. Indonesia appealed, and with the appellate system stalled, that panel report has not become a final adopted ruling. The word weapon captures the pressure. It can also hide the motive. For an importer, a restriction looks like coercion or vulnerability. For a mineral-rich country, it may look like the only tool available to avoid remaining a pit at the bottom of someone else's value chain. That disagreement has triggered the scramble. Governments are responding with a vocabulary once reserved for oil. Strategic reserves, trusted suppliers, emergency authorities, national champions, and security alliances. But unlike building an oil stockpile, rebuilding a mineral chain means recreating many different industries. The European Union's Critical Raw Materials Act set 4 benchmarks for 2030. Where feasible, the EU wants to extract at least 10% of its annual strategic material consumption, process at least 40%, and obtain at least 25% through recycling. At the relevant stage, it wants no more than 65% to come from any single country outside the Union. These are targets, not achievements. They are also not a plan for total self-sufficiency. The point is to make a disruption painful instead of catastrophic. The United States has moved in the same direction. Its final 2025 critical minerals list contained 60 minerals, adding 10 that included copper. Executive actions in 2025 and July 2026 pushed faster domestic production, closer scrutiny of processed mineral imports, and stronger defense acquisition of critical materials. The Department of Defense calls its rare earth effort mine to magnet. As of March 2024, it said it had awarded more than $439 million since 2020 to help rebuild stages from separation to metals, alloys, and magnets. The date matters. An award is not an operating factory, and a 2024 total is not the final cost of the effort. Across advanced economies, public finance commitments for critical minerals reached roughly $65 billion in 2025, more than 4 times the level in 2023. Again, these were commitments, not money necessarily disbursed and not tons already produced. Partnerships are multiplying too. In June 2026, UN Trade and Development counted 58 critical mineral partnerships signed since 2022. Some join mineral producers with the finance, technology, infrastructure, and customers needed to build new chains. Others risk dividing the world into rival blocks that duplicate capacity but still leave poorer producers at the raw material end. That is why the producer's view belongs at the center of the story. Latin America supplies roughly 40% of global copper mine output and about 1/4 of LITHEE mine output. Yet excluding LITHEE, the region refines only about 20% of the key energy minerals it extracts. In an IEA scenario, the region's base project pipeline was worth around $185 billion by 2035. Adding more local refining raised the estimate to roughly $220 billion and nearly 50% more value added. That opportunity is not automatic. Refineries need reliable power, water, transport, skills, customers, stable rules, and environmental safeguards. Forcing local processing before those pieces exist can strand investment. Exporting every unprocessed ton can strand development. Resilience, therefore, has a price. The IEA estimated that holding strategic inventories of 11 high-risk materials outside the dominant supplier could cost less than $900 million a year on a net basis. That is not the price of complete independence. It is the carrying cost of time, enough material to keep essential lines moving while another supplier responds. More mines, more refineries, partnerships, and stockpiles can reduce the danger. But the cheapest ton may still be the ton already inside a product. That is the promise of the second mine. Every battery, motor, cable, and machine is a future or body. The material has already been mined. The rock has already been crushed. Much of the energy and capital needed to concentrate it has already been spent. When the product reaches the end of its life, its copper, Lithium, cobalt, and rare earth material do not stop existing. But recovering them is not as simple as melting everything together. Products must be collected. Batteries must be handled safely. Components must be identified and dismantled. Material is shredded or separated, then chemically recovered and purified to meet manufacturing standards again. A high laboratory recovery rate means little if most products are never collected. Today, recycled sources contribute only about 10% on average across the IEA's key energy minerals. Under current policies, that share could rise toward 20% by 2040. In a more ambitious scenario, the IEA estimated that expanded recycling could reduce the need to develop new mines by 2050 by about 40% for copper and cobalt, and 25% for Lithium and nickel. That is a major strategic resource. It is not the end of mining. The first reason is time. A copper cable may stay in a building for half a century. A vehicle battery remains on the road for years and may find a second use before recycling. During a rapid build-out, far more material enters service than comes out the other end. The stock of machines has to exist before the scrap can return. The second reason is growth. Even an excellent recycling system cannot supply all of a market that is expanding faster than end-of-life material becomes available. And the third reason is another choke point. China holds more than 3/4 of global battery recycling pretreatment capacity and around 90% of material recovery capacity. A circular economy can reproduce the same geographic concentration as the linear one. Recycling works best beside other tools. Products can be designed for disassembly. Manufacturers can use less material. Aluminum can replace copper in some systems. Ferrite or other motor designs can reduce rare earth demand in certain applications. LFP batteries remove cobalt and nickel from the cathode. But every substitution moves the pressure. LFP still needs Lithium, and its supply chain depends heavily on Chinese production of cathode materials and precursors. A motor with fewer rare earths may require more copper, more volume, or a different performance trade-off. There is no dematerialized energy transition. There are better and worse material choices. The second mine is powerful because it changes the geometry of supply. A discarded battery in Europe, a motor in America, or a cable in Africa can become local feedstock instead of a distant deposit. It makes yesterday's imports part of tomorrow's inventory. And it brings us back to the factory where this story began. The missing component finally arrives. The line starts moving. The immediate crisis is over. But nothing about the system has changed if the next component must travel through the same mine, the same refinery, the same port, and the same licensing desk. That is the real meaning of the race. Lithium shows how quickly a strategic market can swing from shortage fear to price collapse and back again. Copper shows how a familiar metal can become the largest volume constraint, trapped behind a 17-year development clock. Cobalt shows two different choke points, mining in the DRC and refining in China, while battery chemistry changes the value of both. Rare earths show that the hardest step may come long after the ore leaves the ground, in the separations, alloys, and magnets that turn chemistry into performance. Under the IEA's current policy scenario, demand for the key energy minerals nearly doubles by 2040, although every mineral follows a different path. That is a scenario, not a prophecy. What does not change is the need for a complete chain. A secure system begins with using material efficiently. It substitutes where performance allows. It builds mines in more than one region and does not stop at the mine gate. It creates competing refineries, separators, cathode plants, alloy makers, and magnet factories. It keeps emergency inventories for the inputs that can stop an economy. It collects products at the end of life and turns them into feedstock again. And it cannot call itself secure if the communities at the beginning of the chain bear all the risk while consumers at the end collect all the value. Mineral-producing countries have a legitimate claim to jobs, infrastructure, revenue, and technical capability. Importers have a legitimate interest in reliable supply. Workers and communities have rights to safe conditions, water, land, consultation, and a voice in decisions that reshape their home. Moving fast without finance or trust can undermine every one of those goals. Resilience is not free. It means paying for spare capacity that may sit partly unused in peaceful years. It means holding inventory instead of optimizing every warehouse to the last day. It means financing projects in new places, accepting higher early costs, and maintaining standards when prices fall. But dependence has a price too. In early 2026, European prices for dysprosium and terbium were roughly 5 times domestic Chinese levels. Sometimes dependence appears as a silent assembly line. Sometimes it appears as foreign policy narrowed by fear of losing a material almost nobody can see. So, who owns the periodic table? No one. Elements cannot be embargoed into or out of existence. Deposits cross borders. Knowledge spreads. Products become scrap. New chemistries redraw demand. But power belongs for a time to whoever controls the hardest junction. The mine that cannot be replaced, the refinery nobody else built, the process few engineers mastered, the component with no substitute, or the stockpile that buys more time. The countries that shape this century will not be those that simply plant a flag over the richest rock. They will be those that build chains other countries trust, that survive shocks without closing themselves off, and that turn mineral wealth into durable human wealth. Oil taught the world to watch the wells, the pipelines, and the straits. The mineral age asks us to look deeper, and then keep following the material after it leaves the ground. Because the map is not the mine. The map is the chain.